Hey class, this is Mrs. Cribb. I need you to take out your notes for Chapter 9 and turn to Section 9.6 on calculations with empirical formulas. You'll also need a calculator, a pen, and your periodic table. I'm going to go ahead and lecture through these notes and fill them in as we go. Just to tell you, this is the part of this particular test for Chapter 9A that will be the most involved, but I know you can do it. So we're going to calculate using empirical formulas. To get the empirical formula and to review, remember that empirical formula or the simplest ratio. So if I had a molecule like C4H6, that could be the molecular formula. Then the empirical formula would be to reduce those. 4 actually goes into both of these, so this would be CH2 would be the empirical formula, the simplest whole number ratio, which is basically reducing the empirical formula to its lowest values. All right, to get the empirical formula, I've given you some basic steps here. It's not always going to be perfect, but it's a guideline. If you have percent composition, you're going to change the percentages given into grams. If you to get a mass composition. If you're already given a mass composition, you can skip that step and you go down to here. The next thing you need to do is change all your grams into moles, and in order to do that, to go from mass to moles, you're going to use the molar mass. And that's on that, remember the little flow chart we've had so far. We can go from mass to moles to particle count. Okay, and so to go from here to there, you need the molar mass, and you get that off the periodic chart. You divide by the smallest mole number after you turn all of them into moles. If the ratio does not have whole numbers, you may need to do some extra math, and we're going to talk about that. And then you'll write the empirical formula. So let me give you a little bit of information. Notice that you will often find it necessary to round slightly to get a whole number. Sometimes your calculation produces ratios like 1 to 1.5 or 1 to 1.33. These should not be rounded off. In general, if the decimal portion of the part of the ratio is greater than 0.1 or less than 0.9, you should not round off. You need to change the decimal to a fraction and fix the problem that way. So what I mean is, first of all, this is called like the no rounding zone right here, the no rounding zone. And what I mean is, let's look at this. The decimal portion, that means this right here, this is 0.25, the decimal portion. If that value falls in the no rounding zone, you don't round. You're going to do some more math. So 0.25 is right here, it's less than 0.9 and greater than 0.1. So do I round this number 1.25? No. No, I don't. All right, the decimal portion here is 0.75. It also falls in the no rounding zone. So I would not round that number. I'd have to do some more math, and I'll show you what that more math is in a minute. 0.33, this is 1.33. The decimal portion right there is still in the no rounding zone, so I do not round this number. I do additional math. Here's the decimal portion of this number, but this is 0.98. It's on this side, 0.98. So yes, I can round this one up. So 1.98 would round to a 2. That would become a 2. 0.92, yes, it's greater than 0.9. So yes, I rounded, and it would also become a 2 because I need whole numbers when working with empirical formulas. All right, we're going to follow these steps, and you're just going to have to watch me and follow along and fill in your notes. And I apologize for the lack of space. So when we get to the bottom one on this one, I want you may need to do it on the back of your paper or on a separate sheet of paper. Okay, we have a laboratory analysis of an unknown gas. We don't know what it is, but we know that this gas is 72.55% oxygen and 27.45% mass. So we're going to figure out the empirical formula, the simplest whole number ratio. Okay, so we have oxygen and carbon. Okay, I'm going to list my carbon first and then my oxygen. Carbon is 27.45% and oxygen is 72.55%. Okay, what's my first step when I have the percentage? Percent composition right here. Change the percentages to grams. Okay, so I'm going to go down here and I'm just going to pretend these are grams. What I'm saying is I don't know how much I have. But if I had 100 grams of it, 27.45 grams would be carbon, and 72.55 grams would be oxygen, because 100%, change that to 100 grams, add these 2 grams together, you get 100 grams. So you just change the percent into grams. That's all you're doing. You just get change in the unit. Now that I have grams, the next step says change your grams to moles right here. Change your grams to moles using the molar mass. So I need to divide carbon by its molar mass, and I need to divide oxygen by its molar mass. So if you look at your periodic chart, and I'll put it up here, there's carbon, 12.01. Remember, I want 2 decimal places. And oxygen is 15.999. We round to 16.00. Okay, whoops, wrong place. There we go. So this becomes 12.01 for carbon and 16.00 for oxygen. So we divide these two, 27.45 divided by 12.01, and I get 2.286 moles. I've just turned it into moles because this is grams per mole right here. Grams per mole. Each one of these is grams per mole. The grams cancel, I end up with moles. So 2.286 moles of carbon, and then 4.534 moles of oxygen. Okay? All right, so that's the next. So first turn the percent to grams, change the grams to moles by dividing by the molar mass, and now I have the number of moles right here. So what's the next step I listed? Divide by the smallest mole number. Okay? So 2.286 is smaller than 4.534. I'm going to mix it up by using green now. So I'm going to divide both of these by 2.286. 2.286. All right, well, obviously 2.286 divided by itself is a 1, because see, I'm looking for a ratio. And 4.534 divided by 2.286 is, let me look at my stuff over here, 1.92. Okay, I'll pull it up on the calculator. 4.534, scooch it over, turn it on, 4.534 divided by 2.286 is 4.534 by 2.286 is 1.983. I must have been looking at something else. 1.983. So let me fix that. Here, I'll erase it. Here we go. 1.983. Okay. So now I have the number of moles, and this point, after I've gotten the moles here and divided by the smallest mole, because both of these are moles, so moles cancel, and I end up with just a ratio. This right here is a ratio, but I want a whole number, so I have to evaluate it, see if I can round it. Now here you go. What's the decimal portion? 0.983. Can I round it? Yes, because that's greater than 0.9. So this rounds to approximately a 2. So this is your ratio. We have carbon, we have oxygen, and we have 1 carbon to 2 oxygens. These are the ratio numbers. The ratio numbers become the subscripts. These become the subscripts of the element above it. So this is CO2. That is my unknown gas, carbon dioxide in this case. And that's assuming that this empirical formula, this is the empirical formula, assuming the empirical formula and the molecular formula are the same this time. All right, now let's try the next one. Here I've already been given mass, nitrogen and oxygen mass. So we're going to calculate the empirical formula this time, starting with the mass. So here's nitrogen and oxygen. Nitrogen is 1.844 grams. And oxygen is 3.156 grams. All right, in both cases, I still need to turn it into moles. See, once I got the mass, I divide by the molar mass to get the number of moles. So I'm going to divide both of these by their molar mass that I get off the periodic table. Nitrogen is 14.01 grams per mole and again the grams will cancel, and I'll end up with moles, and that ends up being 0.1316 moles. And oxygen is 16.00 grams per mole. The grams cancel, and I end up with 0.1973 moles, which is really small. I mean, it's fine, but if you look at it, 1 mole of nitrogen is 14 grams. I only have 1.2. I have a very small amount. And 1 mole of oxygen is 3. And we have 16. I have only 3. So that's why the amount of moles is so small. Okay, what's the next step? What do we do right here? We found the moles, and then we divide by the smallest one. So divide by the smallest, 0.1316 moles. Okay, so remember, we take mass, we turn it into moles, then we divide by the smallest, and that's what I'm doing right there. All right, so this becomes a 1, and this is 1.499. Okay, I'll show you. Scoot it over. Okay, we have 0.1973 divided by 0.1316, and I get 1.499. Okay, all right, now this is where we evaluate it, is the decimal portion in the no rounding zone. Well, what's the no rounding zone again? Just because it's up there above me, it has to be between 0.9. This is the no rounding zone, and then 0.1. It's greater than 0.1 and it's less than 0.9. It's in the no rounding zone. I cannot round. So when I cannot round, here's that extra math. I first turn this decimal into a fraction. So this is about 0.5, okay, 1.5, which would be 1.5. All right, now I'm going to take that 1.5 and turn it into an improper fraction. So 1 times 2 is 2 plus 1 is 3, so 3 halves. Okay, now let's write down the ratio. We have nitrogen and oxygen. Nitrogen is a 1, and oxygen is 3 halves. Okay, we can't have 3 halves of oxygen, so in math we're going to get rid of the fraction. And we're going to get rid of the fraction by taking both of these numbers, these ratio numbers, and multiplying them by the denominator of a 2. So 2 times 1 now becomes 2, and 2 times 3 halves becomes 3, because the 2's cancel out. So now I have the whole number ratio. This is the whole number ratio I need. The ratio becomes subscripts, so this becomes N2O3. That is my unknown compound. This, its empirical formula, N2O3. Okay? All right, there's the extra math right in this area. And then taking it and multiplying it by the denominator. Okay, now let's look at caffeine. We have one more example. And then this is the one where you're probably going to need to do it on another sheet of paper. In fact, I may end up, look at that, stoichiometry is next. That's not until the next test. I'm going to try to fit it on here, but I might use a little bit of this white space down here. All right, caffeine has all these things in it. It has hydrogen, oxygen, nitrogen, and carbon. And it is 5.170% hydrogen. Now, the first step is if you're given the percent by mass, the percent composition, you turn the percent to grams. So I'm not going to write down percentage. I'm just going to turn this into grams. I'm going to turn this one into grams. I'm going to turn this one into grams, and this one into grams. And now I can just write down my grams. 5.170 grams of hydrogen, 16.49 grams of oxygen, 28.86 grams of nitrogen, and 49.48 grams of carbon. Okay, so now I have mass. I turn mass into moles by using the molar mass. So I can look on the periodic table, and I find out the molar mass of hydrogen is 1.01 grams per mole. Grams cancel, and I get 5.12 moles. 3 sig figs because 1.01, but you might use 4 because of this right here. It's not going to make a huge difference on this portion. Oxygen is 16.00 grams per mole. The grams cancel, so we have just moles, and that is 1.031 moles. Nitrogen is 14.01 grams per mole. Grams cancel, we have just moles, and it is 2.060 moles. And carbon is 12.01 grams per mole. Grams cancel, and the answer is 4.120 moles. Okay, so I've turned it into moles. Now the next step, divide by the smallest one. So 1.031 is the smallest one. So I'm going to divide by 1.031 moles all the way down. Okay, 5.12 divided by 1.031 is 4.966, and it's no unit because the moles cancel all the way down. 1.031 divided by 1.031 is 1. 2.060 divided by 1.031 every time is 1.998. And 4.120 divided by 1.031 is 3.996. Now, this is the spot where we evaluate. Look at the decimal portion. Is that in the no rounding zone? No, the 0.966 is greater than 0.9. Remember, no rounding zone. 0.9 is greater than the no rounding zone, which is greater than 0.1. All right, it's in that no rounding. It's not in that no rounding zone. It's bigger. It's bigger than 0.9, so this rounds to 5. This is still 1. This is bigger than the no rounding zone, so this rounds to 2. And this is bigger than the no rounding zone, so it rounds to 4. So what's my empirical formula? HONC. I have 5 to 1 to 2 to 4. 5, 1, 2, 4, HONC. It has to be in the same order, HONC, that you wrote down. So H5O2N2, I wrote a 2, I might need to write N first. N2C4. That's the empirical formula. Now, it's not in the right order, but that's okay for this kind of thing. Sometimes you'll be able to figure out what the right order is. Now, this is not asking for the empirical formula. It's asking for the molecular formula. Okay? So this one involves the most math. The next thing I need to figure out is the empirical mass. EM is what I'm going to call it. The mass of the empirical formula. So it's just like the molar mass, except it's just the mass of what's here. So I list them all again, and I figure out the mass this time. We have 5 hydrogens, 1 oxygen, 2 nitrogens, and 4 carbons. Okay, right here. 5, 1, 2, 4. Okay, multiply all of these by their molar masses because we're figuring out the mass. Okay, the mass. So hydrogen is 1.01, oxygen is 16, nitrogen is 14.01, and carbon is 12.01. Remember, all of these come from the periodic table. Carbon, nitrogen, oxygen, hydrogen, all of them. You're looking at the mass, the 1.01. Remember, we're rounding to 2 decimal places. Okay? So, multiply these through. I get 5. Okay, write that again. 5.05 for hydrogen. Oxygen is 16. Nitrogen is 28.02. and carbon is 48.04. Okay, I'm going to add all those together, and I ended up getting 97.11 grams per mole. This number right here is the empirical mass, the mass of the empirical formula. All right, so we're getting there. We're almost done now. In order to calculate the molecular formula, what I do, the molecular formula is going to be equal to the empirical formula, and then we're going to multiply by each of the subscripts by n. Okay, that means, so we got to figure out what n is. And n is just a ratio. So n is equal to the molecular mass, the molar mass, divided by the empirical mass. Okay, they told me right here the molar mass of caffeine is 194.20 grams per mole. So 194.20 grams per mole divided by the empirical mass, which is right there. We just calculated it, 97.11 grams per mole. Notice that the units cancel completely. And so what is this number? The n is just a multiplication factor. The n is a multiplication factor, okay? And a multiplication number. So when I divide those out, I get approximately 2. That's the n. So the molecular formula is the empirical formula where I multiply the subscripts by the n value. So the empirical formula was right here. I'm going to have to write this down here now, guys, okay? I'm going to move it up just a little bit because I'm running out of space. So here's the empirical formula was H5ON2C4. Now I'm going to multiply all the subscripts by the 2 that we just figured out. All the subscripts by 2. So this is going to equal the molecular formula, which is equal to 2 times 5, H10, 2 times 1, O2, 2 times N, N4, and 2 times 4, C8. So this is the molecular formula. That would be the final answer. Now I'm going to show you caffeine. Now I'm going to rewrite this in the order that it is normally. It would be C8, H10, N4, O2. See, I just rewrote them, changed the order. This is the caffeine molecule. What we did was we took the masses given, we divided by the molar mass, divide by the molar mass to get a number of moles. We divided by the smallest number of moles to get a ratio. The ratio is where I get the empirical formula from. The ratio is the subscripts. The ratio are the subscripts for the empirical formula. Then we calculated the molar mass of the empirical formula, or the empirical mass, and then we calculated this number here, n, which is just a multiplication factor. Once we know that multiplication factor, we take the subscripts of the empirical formula and multiply it by that multiplication factor to come up with the molecular formula. So there's caffeine. Let me show you caffeine on the website now. There it is. There's the caffeine molecule. And there's the formula, C8H10N4O2. That's the molecular formula. Notice there's the molecular mass, or the molecular weight, 194. Our problem said 0.20. This one says 0.194. And just so you know, here's the structure of the molecule. This would be the structural formula. All the gray balls that you see are carbons. So 1, 2, 3, 4, 5, 6, 7, 8 carbons. The red ones are the nitrogens, okay? The hydrogens are the little bitty gray ones. Little bitty ones down here. And so what am I missing? Where's the oxygen? Somewhere in here there must be an oxygen that I don't see. Magnify. Oh, well, I'm not going to worry about it right now. All right. So go back to this. So that's where our notes end for Chapter 9A. All the test will be on just Chapter 9A, and we'll start Chapter 9B after we test on 9A. Okay, hopefully you have this. See you soon.